Hello, and welcome to Bedside Physics, where we embark on soothing yet fascinating journeys through the cosmos. Before we drift into the depths of the universe, make sure to like and subscribe so you never miss an adventure in the world of science. And, if you're settling in for a cozy listen, let me know where you're watching or listening from. Whether you're curled up in bed or gazing at the stars, it's always interesting to hear how far and wide these cosmic questions travel. Now, as we dive into today's exploration, imagine this. What if everything we know about the universe's beginning is only a part of a much bigger story? What if the Big Bang wasn't the beginning at all? Could there have been something, or perhaps someone, before the birth of space and time? Is it even possible to think about before time as we understand it? Tonight, we'll unravel some of the most profound mysteries about the universe's origins. From quantum fluctuations to mysterious multiverses, we're about to step into a world where time itself might have never existed, and our universe might just be one chapter in an infinite cycle of creation and rebirth. So, relax, open your mind to the cosmic possibilities, and let's start our journey into the universe before the Big Bang. What came before the Big Bang? It's one of the most profound questions in all of cosmology, and one that has puzzled scientists and philosophers for centuries. We've spent so much time focusing on the Big Bang itself, that incredible moment when our universe began expanding from an infinitely dense point about 13.8 billion years ago. But what happened before that? Was there anything? And perhaps more intriguingly, is it even possible to talk about a before? To understand why this is such a tricky question, let's first acknowledge what we know. The Big Bang Theory, which explains how our universe expanded from this minuscule, hot and dense state, is widely accepted as the foundation of modern cosmology. But here's the thing, the very concept of the Big Bang is based on the assumption that time and space as we understand them began with the event itself. So, asking what happened before the Big Bang presents a kind of paradox, because according to the theory, time itself is said to have started with that very moment. It's almost like trying to ask what's north of the North Pole, or what happens on the other side of the edge of the universe. These are questions that arise out of the limits of our understanding, and they can feel like a bit of a dead end. But that's also where the excitement comes in. We might be pushing against the boundaries of conventional knowledge, but that's how we make progress in science. For centuries, we've relied on certain fundamental principles in cosmology, grounded in Einstein's theories of relativity, which suggest that time, space, and gravity are intertwined. According to Einstein's general theory of relativity, the very fabric of space and time itself can bend, stretch, and warp under the influence of mass and energy. But when we try to apply these principles to the beginning of the universe, we hit a wall. General relativity predicts that the universe originated from a singularity, a point where the curvature of space-time is infinite, but singularities break the rules of physics. They represent a place where our current understanding simply doesn't apply. It's as if the very laws we depend on start to break down in the face of the universe's origin. This is why it's so crucial to explore uncharted ideas in cosmology. We know that our current models of physics aren't enough to explain the universe's true beginnings, and that's why theorists and physicists are pushing for new ideas, new frameworks, and new approaches. When we look at these new theories, we're not just imagining wild concepts for fun, we're trying to find the next big leap in our understanding of the cosmos. Ideas like quantum gravity, multiverses, and the possibility of pre-Big Bang phases challenge everything we think we know about space, time, and causality. They invite us to think beyond the familiar and explore ideas that, while speculative, could open up entirely new avenues of understanding. One such idea is the concept of quantum cosmology, where scientists like John Wheeler and Stephen Hawking explored the idea that the universe's birth could have been a quantum event, governed by the strange, unpredictable rules of quantum mechanics. In this framework, the early universe could have emerged from a quantum fluctuation, a tiny disturbance in the fabric of space-time that spontaneously created the Big Bang itself. This theory suggests that the laws of classical physics don't apply to the earliest moments of the universe, and when you start to entertain these possibilities, you're not just asking what happened before the Big Bang, you're asking what laws govern that before, and whether before even makes sense. Then there's the idea of a cyclic universe, a theory that has roots in both ancient philosophy and modern physics. Instead of a single Big Bang marking the birth of everything, This theory proposes that the universe goes through an endless cycle of birth, death, and rebirth. The universe expands, contracts, and then expands again, with each Big Bang being a restart of an eternal process. Scientists like Roger Penrose have developed models around this, suggesting that the universe may not have a single, definitive beginning. Instead, it may be part of a cosmic loop that stretches back far beyond our understanding. These ideas stretch our imagination, but they also keep us grounded in the knowledge that there's more to learn. The work of modern physicists like Andre Linde, who pioneered the theory of inflationary cosmology, provides further insight into how our universe might have come from a quantum fluctuation, a tiny, fluctuating pocket in a larger, unseen multiverse. The universe we see around us could simply be one of many, each with its own Big Bang and unique set of laws. In fact, the multiverse theory, which suggests that there are infinite universes, each with its own physical laws and constants, offers a fascinating possibility. What if our Big Bang wasn't the only one? What if our universe was simply one bubble in an infinite sea of universes? Each of these universes could have its own Big Bang, each with different rules of time and space. While still a speculative idea, the multiverse theory forces us to think beyond the confines of our universe and ask questions we've never considered before. So as we set the stage for our journey into the cosmos, it's important to acknowledge that while much of what we'll explore is theoretical, these ideas are grounded in the best available scientific thinking. Theories about the universe before the Big Bang may seem strange and even unsettling, but they push us to reconsider the very nature of reality itself. We're no longer just exploring the past of our universe, but considering what could lie beyond the boundaries of time, space, and even our own understanding of causality. The more we push these boundaries, the more we'll uncover. So, as we dive deeper into these possibilities, let your mind wander freely through the vastness of the cosmos. The universe is full of mysteries, and sometimes asking the right question is the first step toward unlocking the greatest discoveries of all. For much of human history, the universe was understood through the lens of classical physics. It was an elegant, structured view of the cosmos that seemed to explain everything around us. Under the framework of Newtonian mechanics, we understood motion, gravity, and the behavior of objects in space. In this worldview, the universe was seen as a vast, orderly machine, predictable, consistent, and timeless. In the Newtonian model, the universe was thought to be infinite, static, and unchanging. The laws of motion, which Sir Isaac Newton famously formulated in the late 17th century, described the way objects moved in space with remarkable precision. Newton's law of universal gravitation, which states that every mass attracts every other mass with a force proportional to the product of their masses, and inversely proportional to the square of the distance between them, gave us the ability to predict the movement of planets, moons, and even comets with astonishing accuracy. For a long time, this view of the universe made sense. The cosmos appeared to be a grand mechanical system, governed by well-defined laws. But as our understanding of the universe deepened, it became clear that classical physics could not explain everything. The most obvious problem arose when we turned our attention to the origin of the universe itself. Classical physics, with its neat and tidy laws of motion, failed to explain how the universe could have come into existence. If the universe was simply a vast collection of matter governed by predictable forces, then how could it have originated from a singular point, a beginning that was infinitely dense, infinitely hot, and infinitely small? The very idea of an origin, a point of creation, seemed to contradict the framework that Newtonian physics provided. Classical physics, in its purest form, had no answer for the Big Bang. Enter the early 20th century, when the next major revolution in our understanding of the cosmos was about to unfold. A new, mind-bending theory began to emerge, one that would upend everything we thought we knew about physics and the universe's origin. This new framework was born out of the breakthroughs in quantum mechanics, the science that describes the behavior of matter and energy on the smallest scales. Quantum mechanics challenged the very foundations of classical physics, showing us that the universe is not as predictable or mechanical as we once believed. The transition from classical to quantum thinking marked a profound shift. In the classical world, objects were treated as individual, separate entities that behaved according to fixed laws. But in the quantum world, particles and waves were not always distinct. They were both at once. matter could exist in multiple states simultaneously, and the act of observing something could alter its behavior. This uncertainty, famously described by Werner Heisenberg's uncertainty principle, shattered the neat deterministic framework of Newtonian physics. When it came to explaining the origin of the universe, quantum mechanics introduced a whole new set of possibilities. Instead of a static, predictable universe, quantum theory suggested that at the smallest scales, the universe was governed by probabilities and uncertainties. It was this unpredictability that allowed for the possibility of a universe emerging from a quantum fluctuation, a spontaneous random event in which space-time itself could come into existence. It was no longer necessary to think of the universe as having a singular mechanical origin. Rather, it could be born from quantum uncertainty, an idea that Einstein himself struggled to accept. Although Albert Einstein's theory of general relativity, which describes the force of gravity and the curvature of space-time, was groundbreaking, it still relied on the concept of a singularity. At the centre of every black hole, for example, general relativity predicted that the curvature of space-time would become infinite, forming a point of infinite density where the laws of physics break down. This idea seemed to fit with the Big Bang model, suggesting that the entire universe might have originated from such a singularity. But even Einstein recognized that general relativity couldn't fully explain what happened at this point. It was physicists like Arthur Eddington who first began to question the capacity of classical physics to account for cosmological origins. In the early 20th century, Eddington, an English astronomer and physicist, was one of the first to suggest that the universe was not an entirely predictable machine. He recognized that the cosmos had a deeper, more complex nature, one that classical physics could not fully comprehend. Eddington, along with others, pondered whether the laws of classical physics could be stretched to explain the origin of the universe, or whether a completely new way of thinking was required. This uncertainty and the realization that classical physics was insufficient led to the development of new ideas, including the birth of quantum cosmology. One of the key proponents of this new approach was the brilliant mathematician and physicist Kurt Gödel, who began to explore solutions to Einstein's equations of general relativity that allowed for a universe without a beginning. Gödel's work hinted at the possibility that time itself might be more complex than we had ever imagined, possibly even cyclical, or existing in a form that doesn't conform to the classical linear progression we're used to. As the years progressed, the discovery of cosmic microwave background radiation, the afterglow of the Big Bang, provided evidence for the model of an expanding universe. Yet, this discovery also revealed that our classical ideas about the universe's origin were deeply flawed. The universe, it seemed, wasn't static or eternal. It was dynamic, constantly expanding from an initial point. This realization made it clear that the classical model could not explain this origin, pushing scientists to search for new, more robust frameworks. Quantum mechanics opened the door to possibilities that classical physics had never dreamed of. The universe could have originated not from a singular, defined point, but from a quantum fluctuation, an event that didn't require the traditional laws of physics to apply. The very fabric of space-time could have emerged from an unstable state, with time itself becoming part of the equation. This leap in thinking, which would eventually give rise to quantum cosmology, was a revolution that not only changed our understanding of the universe's origin, but also reshaped the entire field of physics. The limits of classical physics had become clear. It simply couldn't explain the origin of the universe. But in breaking through those limits, scientists began to explore new dimensions of possibility, driven by quantum mechanics, relativity, and an openness to ideas that were, at first, nearly unimaginable. And in doing so, they began to uncover a universe much more strange, mysterious, and wondrous than we had ever thought possible. For centuries, we've lived with a fairly simple understanding of time. It's a constant, a straight line stretching from the past, through the present, and into the future. We measure it in seconds, minutes, hours, and years, and it governs everything from the ticking of a clock to the turning of the seasons. But what if time, as we know it, didn't exist at all before the Big Bang? What if time itself was not a fundamental part of the universe, but something that emerged from the very birth of the cosmos? This idea is at the heart of one of the most fascinating areas of modern theoretical physics, quantum gravity. Quantum gravity seeks to combine two of the most successful theories in physics, general relativity and quantum mechanics, into one unified framework. General relativity explains how massive objects like stars and planets warp the fabric of space-time, while quantum mechanics governs the behavior of the very smallest particles in the universe. But the problem is that these two theories don't play well together when it comes to describing extreme conditions like the beginning of the universe. At the heart of quantum gravity is the notion that space-time itself might not be a smooth, continuous entity, as we traditionally think of it, but instead a kind of quantum foam, a fluctuating dynamic field that exists in discrete chunks, much like the behavior of particles in quantum mechanics. This idea suggests that space and time themselves could be emergent, meaning that they didn't exist in the way we understand them until the very moment of the Big Bang. One of the leading figures in this line of thinking is Carlo Rovelli, an Italian theoretical physicist known for his work on loop quantum gravity, or LQG. Rovelli's ideas challenge the classical view of time and space, proposing that time, much like space, may not be a fundamental building block of the universe, but instead something that arises from more basic interactions. The central idea of Rovelli's work is that time, as we perceive it, is not something that exists independently of the universe. Rather, time might be a byproduct of the physical processes within the universe itself. In the framework of loop quantum gravity, space-time is made up of tiny loops of energy, almost like a fabric woven together by the forces of the universe. These loops are constantly changing, interacting with one another, and evolving, creating the experience of what we perceive as time. This concept of time as an emergent phenomenon is quite radical. According to Rovelli and his colleague Lee Smolin, who has also made significant contributions to the development of LQG, time doesn't exist in the traditional sense at the Planck scale, the incredibly small scale where quantum effects are most pronounced. Instead, at that scale, there are no traditional notions of past, present, or future. Time doesn't flow as we experience it in our daily lives. Rather, it is a more fluid and subtle feature that arises from the interactions of the fundamental building blocks of the universe. But what does this mean for our understanding of the universe before the Big Bang? If time itself is emergent, then it may be more accurate to say that there was no before the Big Bang in the conventional sense. There was no time as we know it. Instead, the Big Bang represents the moment when time, along with space, began to take shape. This implies that asking about the state of the universe before time began may be a bit like asking what's north of the North Pole. It's a question that doesn't really have a meaningful answer within the constraints of our understanding of physics. The implications of this idea are profound. If time is truly emergent, then the classical idea of a singular beginning to the universe, marked by the Big Bang, may need to be re-examined. Perhaps the universe didn't start in the way we traditionally think. Instead of a sudden, explosive event, the emergence of time and space could have been part of a more gradual process, where quantum mechanics and the laws of physics gradually created time as we know it. In this view, the Big Bang wasn't so much a beginning as it was the moment when time, and all the physical laws we know, emerged from a prior state of pure quantum potential. This shift in thinking also raises the possibility that the universe is not a one-time event, but part of a cycle, a never-ending process where time and space emerge, evolve, and then potentially collapse back into some other form. This idea has been explored through models like the cyclic universe theory, where each Big Bang is followed by a big crunch, only to start over again in an eternal cycle. In this view, the origin of the universe is not a unique event, but just one iteration in an infinite series of cosmic rebirths. The potential of loop quantum gravity to reshape our understanding of space-time goes beyond just time as an emergent phenomenon. LQG suggests that space itself is not a smooth, continuous fabric, but rather it is made up of discrete indivisible units, much like the way light behaves in quantum mechanics. These units of space are incredibly small, on the scale of the Planck length, which is around 10 to the minus 35 meters. At this scale, space is no longer a smooth continuum, but a collection of tiny loops, each representing the most fundamental building blocks of the universe. This discrete nature of space-time implies that, at extremely small scales, the concepts of time and space might behave in ways that are radically different from anything we experience. In this picture, the classical notion of a smooth, continuous flow of time simply doesn't apply. Instead, time could emerge as a series of discrete events or moments, each one shaped by the underlying quantum fabric of space. One of the most fascinating implications of loop quantum gravity is that it may provide a way to reconcile general relativity and quantum mechanics, two theories that, until now, have been difficult to unite. General relativity explains the behavior of massive objects and the structure of space-time, while quantum mechanics deals with the smallest particles of nature. But these two frameworks don't mesh well when it comes to understanding the very beginning of the universe, where both gravitational forces and quantum effects would have been at their most extreme. LQG offers a potential solution by suggesting that space-time itself is quantized, which would mean that at the Planck scale, space and time behave in discrete rather than continuous ways. This could allow us to understand the very fabric of the universe at its most fundamental level, and, possibly, provide a unified theory that explains both the large-scale structure of the cosmos and the behavior of subatomic particles. In the end, the concept of time as an emergent phenomenon forces us to think about the universe in an entirely new way. Time, space, and even the very laws of physics might be far more fluid and dynamic than we've ever imagined. The Big Bang, rather than marking the beginning of everything, could have been the moment when time itself emerged, and with it, the structure of the universe as we know it. Time may not have existed before that moment, and the question of what came before the Big Bang may simply be a question without meaning in the context of our current understanding of the universe. When we think about the origin of the universe, the idea of the Big Bang is likely the first thing that comes to mind, that singular moment, about 13.8 billion years ago, when the universe began expanding from an infinitely hot and dense point. But what if the Big Bang wasn't the true beginning of the universe? What if it was simply the latest in an endless cycle of expansion and contraction? This idea is at the heart of the Big Bounce theory, which suggests that the universe goes through an eternal series of birth and rebirth, contracting, collapsing, and then expanding again in a never-ending cosmic cycle. The Big Bounce challenges the conventional Big Bang model by proposing that the universe didn't start with a single, unique explosion. Instead, the Big Bang we observe could be the latest phase in a much older cyclical process. According to this theory, after each expansion phase, the universe eventually slows down, contracts, and eventually collapses back on itself, only to begin expanding again. This process could have been going on for an infinite amount of time, with no clear beginning to the universe. One of the leading proponents of this idea is the British physicist Roger Penrose. Penrose, a name that has been synonymous with groundbreaking contributions to physics, has developed a theory known as conformal cyclic cosmology, or CCC. In this model, the universe goes through an infinite series of cycles, each marked by its own Big Bang. These cycles, according to Penrose, are connected by the concept of conformal geometry, which allows the structure of the universe to transition smoothly from one cycle to the next, even as it expands and contracts. Penrose's CCC suggests that the universe we live in is only one of many iterations of the cosmos. Each cycle begins with a Big Bang, followed by a period of expansion, and ends with the universe becoming smooth and empty. The transition from one cycle to the next happens when the universe reaches a stage where it is almost devoid of matter and energy, leaving only the radiation that remains after the previous expansion. In this view, the Big Bang is not a singular event, but part of an ongoing process that stretches infinitely into the past and the future. Penrose's theory is certainly intriguing, but it raises a number of questions. If the universe is cyclic, what caused the first Big Bang? Was there a time when the cycle started? And perhaps most importantly, how can we test the existence of previous cycles if there's no physical evidence from earlier universes? While these questions remain unanswered, Penrose's ideas open up a fascinating new perspective on the nature of the universe and its origins. At the same time, other physicists such as Andre Linde have proposed a similar idea in the form of the pre-Big Bang model. Linde, one of the pioneers of inflationary cosmology, is best known for his work on the theory of cosmic inflation, which suggests that the universe expanded at an extraordinarily rapid rate just moments after the Big Bang. However, Linde's pre-Big Bang model extends this idea further, suggesting that the universe may have existed in some form before the Big Bang, and that this early phase could have played a crucial role in shaping the universe as we know it today. In Linde's view, the universe might have started from a previous phase of cosmic inflation, driven by a form of energy that caused the universe to expand at an accelerated rate. This would have been followed by a more gradual phase of expansion, leading to the universe we see today. The pre-Big Bang model suggests that the universe is part of an eternal process of inflation and contraction, where each phase of expansion is followed by a new phase of cosmic growth. These ideas not only challenge the traditional understanding of the Big Bang, but they also raise deep philosophical questions about the nature of time and causality. If the universe is part of a never-ending cycle, with no true beginning or end, what does that mean for our understanding of time itself? Is time infinite, or is it something that emerges from the physical processes of the universe? And if the universe has always existed in some form, what does that mean for the concept of a creation event, or the idea of a creator? Quantum gravitational models, such as those inspired by loop quantum gravity, LQG, also offer insights into the possibility of a cyclic universe. LQG is a theory that aims to merge quantum mechanics with general relativity, explaining the behavior of gravity at the smallest scales of space-time. According to LQG, space-time is not a smooth, continuous fabric, but is instead made up of tiny, discrete units, much like the way matter is made up of atoms. At the Planck scale, the smallest scale of space-time is thought to be quantized, with each tiny unit of space-time interacting with others in a complex dynamic way. In the context of the Big Bounce, LQG suggests that the universe's collapse into a singularity might not be inevitable. Instead, quantum gravitational effects could cause the universe to bounce back from a collapse, avoiding the formation of a singularity and leading to a new phase of expansion. This idea is supported by the work of physicists like Abhay Mehta and others who have developed models of quantum gravity that allow for such a bounce, where the universe transitions smoothly from one phase to the next without the need for a singular beginning. What's especially fascinating about these quantum gravitational models is that they suggest the universe could have had no beginning in the traditional sense. Instead of originating from a singularity or a Big Bang, the universe could have emerged from a quantum fluctuation or a transition between different phases of space-time. This challenges the classical notion of a creation event, suggesting that the universe may be eternal, cycling through periods of expansion and contraction, each phase giving rise to a new version of the cosmos. Philosophically, the idea of a cyclic universe has profound implications. It forces us to reconsider our understanding of time, causality, and the nature of the universe itself. If the universe is part of an eternal cycle, then the concept of a singular origin loses its significance. The idea that the universe has always existed in some form and will continue to exist in different forms indefinitely challenges our very understanding of existence. Ultimately, the Big Bounce theory, along with models like Penrose's conformal cyclic cosmology and Linde's pre-Big Bang idea, invites us to think more deeply about the universe and our place in it. Rather than viewing the universe as a one-time event that began with the Big Bang, these theories suggest that the universe may be part of an eternal cyclical process, one that spans across infinite time and multiple iterations of creation. While these ideas remain speculative, they offer a fresh and exciting way to think about the origins of the cosmos and the fundamental nature of reality itself. Imagine, if you will, an entire ocean of universes, each with its own distinct properties, laws of physics, and even dimensions of space and time. You might think this sounds like the stuff of science fiction, but it's a concept that has become increasingly plausible in modern physics: the multiverse. The multiverse theory proposes that our universe is just one of many, perhaps an infinite number, that exist within a much larger, broader cosmos. But what does this mean for the nature of reality itself? What does it say about our place in the cosmos? The multiverse raises profound questions, but also opens the door to an entirely new way of thinking about existence. Rather than imagining our universe as the only one, an isolated pocket of space and time, the multiverse suggests that countless other universes could exist, some similar to ours and others completely different. One of the most well-known ideas in the multiverse family is the concept of an inflating multiverse. This idea is closely tied to the theory of cosmic inflation, which was first proposed by the physicist Alan Guth in 1980. Guth's theory of inflation suggests that just moments after the Big Bang, the universe expanded exponentially, far faster than the speed of a light, in a tiny fraction of a second. This rapid expansion explains many of the features of the universe we see today, such as its large-scale uniformity and flatness. But Guth and other cosmologists soon realized that the process of inflation could be even more profound than initially thought. If inflation could occur in one region of the universe, why couldn't it happen in other regions as well, in parallel? This is where the idea of the inflating multiverse comes in. Instead of one single universe expanding from a singular point, inflation could be happening continuously, creating pockets of space-time, each one expanding into its own universe. These bubbles could be completely separate from one another, each governed by its own set of physical laws. The inflating multiverse model suggests that our universe is just one bubble in a much larger, ever-expanding cosmic foam. Each universe within this multiverse could have its own version of physical constants, like gravity, the speed of light, or the strength of electromagnetism. Some of these universes might be remarkably similar to our own, with stars, galaxies, and planets. Others, however, could be wildly different, with entirely different rules of physics that might make life as we know it impossible. This theory radically alters our understanding of what reality means. If there are infinite universes, each with its own physical laws, then the very idea of the universe begins to lose its meaning as we understand it. Our universe could simply be one chapter in an endless cosmic narrative, and the laws of physics that we rely on, the laws that govern everything from atoms to galaxies, might just be one set of rules among many. But the inflating multiverse is not the only model of the multiverse. Another compelling interpretation is the many-worlds hypothesis, which arises out of the realm of quantum mechanics. According to quantum mechanics, particles don't just exist in one state. Instead, they exist in a range of possible states, and it's only when we observe or measure them that they collapse into a single, definite state. This creates what's known as quantum superposition. The many-worlds interpretation of quantum mechanics takes this idea one step further. It suggests that instead of a single particle collapsing into one state, every possible outcome of a quantum event actually happens, but in different parallel realities. Imagine you flip a coin. In one world it lands heads up. In another, it lands tails up, and in an infinite number of other worlds it could land in any number of other possibilities. In this view, every time a quantum event occurs, the universe splits into multiple parallel worlds, each with its own version of reality. If this interpretation is correct, then the many-worlds hypothesis suggests that every possible outcome of every decision, every event, and every quantum interaction is realized in its own separate universe. This doesn't just apply to tiny particles, it could extend to everything in the universe. Every time you make a choice, every possible version of yourself, every possible timeline exists in a parallel universe. From this perspective, the multiverse is not just a collection of random universes, but a constantly branching tree of possibilities, each one representing a different version of reality. Then there's the string theory-based version of the multiverse, known as the landscape multiverse. String theory, which attempts to describe all fundamental forces and particles in terms of one-dimensional strings, predicts the existence of extra dimensions beyond the three that we experience in daily life. In string theory, these extra dimensions could be compactified, meaning they are curled up so small that we cannot perceive them. One of the predictions of string theory is that there could be a vast number of ways that these extra dimensions can be configured, each configuration giving rise to a different set of physical laws. In the landscape multiverse, each possible configuration of the extra dimensions creates a separate universe, with its own unique set of laws and constants. There could be an almost infinite number of universes, each one with different rules governing everything from the strength of gravity to the properties of elementary particles. Max Tegmark, a physicist and cosmologist, has taken this idea even further. He proposed a classification scheme for different levels of the multiverse. Level 1 is the inflating multiverse we discussed earlier, where multiple universes arise from inflation. Level 2 includes universes with different physical constants, as predicted by string theory's landscape multiverse. Level 3 is the many-worlds interpretation of quantum mechanics, where every quantum event leads to the creation of new universes. And Level 4, the most radical of all, suggests that all mathematically possible structures, all possible sets of physical laws, might exist in their own separate universes. In this view, the multiverse is not just infinite in number, but infinite in variety, containing every conceivable version of reality. The speculative potential of quantum fluctuations generating entire universes is another fascinating aspect of these multiverse models. Quantum fluctuations are tiny, random changes in energy that occur at the smallest scales of space and time. These fluctuations can, in theory, create pocket universes, regions of space-time where the laws of physics operate in entirely new ways. In this view, the creation of a new universe could be nothing more than the result of a quantum fluctuation, a random, tiny fluctuation in energy that gives rise to an entirely new reality. While these ideas may sound far-fetched, they have gained traction among physicists and cosmologists because they emerge naturally from the equations of quantum mechanics, string theory, and cosmology. They offer elegant solutions to some of the deepest questions about the nature of reality and the universe's origins. The multiverse, once thought to be the stuff of science fiction, is now considered a serious and scientifically grounded hypothesis. Ultimately, the multiverse theory challenges everything we thought we knew about the universe. If there are infinite universes, then the very concept of the universe becomes less meaningful. Perhaps our universe is just one tiny bubble in a vast, ever-expanding multiverse, and the laws of physics that we rely on are merely one set of possibilities among many. This idea not only expands our understanding of the cosmos, but it also forces us to reconsider what it means to be alive, to exist in this particular universe, at this particular point in time. As we look out into the vastness of space, we may also be looking into the infinite possibilities of reality itself. When we look out into the night sky, we see galaxies, stars, and nebulae, all the familiar structures that make up our universe. But the truth is, most of the universe remains invisible to us. Around 85% of the mass of the universe is made up of something we can't see or directly detect. This mysterious substance is called dark matter, and it's one of the greatest unsolved mysteries in modern cosmology. Alongside dark matter, there is another enigmatic force at play, dark energy, which makes up roughly 70% of the energy density of the universe. These two phenomena, though invisible and largely mysterious, may hold the key to understanding not just the present-day universe, but its very origins, including the time before the Big Bang. Dark matter, as the name suggests, doesn't emit, absorb, or reflect light, which is why it's so elusive. We can't see it directly, but its presence is felt through its gravitational effects on visible matter. For instance, when scientists observe galaxies, they notice that the stars on the outer edges of galaxies are moving faster than they should be, based on the visible mass in the galaxy. It's as if there is more mass in these galaxies than we can see, and that unseen mass is dark matter. This gravitational pull is also responsible for the way galaxies cluster together. The forces we can observe simply don't add up without accounting for dark matter's influence. But dark matter isn't just a modern mystery. It has played a crucial role in shaping the structure of the universe. In the early stages of the universe, dark matter's gravitational pull was a vital factor in the formation of galaxies and clusters of galaxies. It acted like a scaffolding, drawing in normal matter and providing the gravitational well from which stars and galaxies could form. Without dark matter, the universe might not have the structure we see today. It might not have been able to form the galaxies, stars, and planets that are so familiar to us. Even more intriguing is the possibility that dark matter, along with dark energy, might have played a role in the pre-Big Bang state of the universe. Some theories suggest that dark matter could have existed in a different form prior to the Big Bang, influencing the evolution of space-time before the universe began to expand. In these models, dark matter could have been present in the early universe, contributing to the conditions that eventually led to the Big Bang. On the other hand, dark energy, that mysterious force responsible for the accelerated expansion of the universe, is a force that works in the opposite direction. While gravity pulls matter together, dark energy pushes it apart. This expansion is happening at an accelerating rate, and scientists believe dark energy is responsible for this. Dark energy's influence is strongest on the larger scales of the universe, where it drives galaxies apart, counteracting the effects of gravity. But what if dark energy didn't just start influencing the universe after the Big Bang? What if it played a role in triggering the Big Bang itself? There's a speculative theory that proposes dark energy could have been present in a different form before the Big Bang, in a state where it drove the universe's initial expansion, essentially acting as the catalyst that started the whole process. In this view, The energy responsible for the rapid expansion during the Big Bang could have been the same force that is now causing the accelerated expansion of the universe today. In fact, some quantum gravitational models suggest that dark energy's influence might have been felt even before the universe's birth, perhaps as part of the mechanism that generated the Big Bang. It's possible that in the earliest moments of the universe, dark energy could have been a key factor in initiating the rapid expansion of spacetime, pulling the universe from an infinitesimally small and dense state to the vast cosmos we now observe. This would make dark energy not only a current force shaping the future of the universe, but also a critical force in its beginning. But the role of dark matter and dark energy isn't confined to simply influencing the early stages of the universe. These forces could also have provided the conditions for the emergence of the universe itself, even before the Big Bang. In some models of quantum gravity, it is proposed that dark matter and dark energy were present in some form, possibly as fluctuations in the quantum vacuum that gave rise to the Big Bang. Quantum fluctuations are tiny, random fluctuations in the fabric of spacetime, which occur at the smallest scales of energy. These fluctuations are responsible for many phenomena in quantum mechanics, and they could have played a fundamental role in the creation of the universe. In this view, the Big Bang wasn't just an isolated event, but rather a quantum transition from one state of spacetime to another. The birth of the universe might have been the result of a quantum fluctuation in the very fabric of spacetime, where the energy stored in dark matter and dark energy was released, triggering the expansion of the universe. This idea is speculative, but it's based on the notion that quantum fluctuations are a fundamental part of the universe's structure, and that they may have existed in some form before the Big Bang. The speculative nature of these ideas is part of what makes them so intriguing. Because dark matter and dark energy cannot be directly observed, their role in the universe's origin remains a mystery. Scientists continue to search for evidence of their influence, and experiments like those at the Large Hadron Collider and the study of cosmic microwave background radiation are helping to shed light on their properties. But the real challenge is understanding how these invisible forces that seem to operate on scales beyond our direct perception, might have played a role in the creation of the universe. One of the most exciting aspects of these theories is their connection to quantum gravity. Quantum gravity is an attempt to reconcile the two major pillars of modern physics: general relativity, which describes the behavior of large objects like stars and galaxies, and quantum mechanics, which governs the behavior of tiny particles. When it comes to understanding the very early universe, these two theories need to work together, and quantum gravity could provide a framework that explains how dark matter and dark energy were involved in the formation of space-time itself. It might help us understand how the universe was born from a quantum fluctuation, where both dark matter and dark energy played crucial roles. In the end, dark matter and dark energy are not just concepts that help us understand the present universe. They may also be the key to unlocking the deepest mysteries of the universe's past. If these invisible forces were at play in the pre-Big Bang state, they could offer answers to some of the most profound questions in cosmology. How did the universe begin? Was there a state of before the Big Bang? And what role did these enigmatic forces play in the cosmic birth of our universe? While we may not yet have all the answers, dark matter and dark energy continue to be at the forefront of our search for the origins of the cosmos, guiding us toward new possibilities and new understandings of the universe's true nature. Imagine for a moment that the entire universe, as we know it, emerged not from a singular explosive event, but from a seemingly empty vacuum. This might sound strange, especially when we've grown so accustomed to thinking of the Big Bang as the start of everything. But in quantum mechanics, things are not always as straightforward as they seem. What if, instead of a singular, well-defined beginning, the universe arose from the very fabric of quantum uncertainty? This idea challenges our traditional notion of a singular beginning for the universe, which we typically associate with the Big Bang. What if the Big Bang was not a true beginning, but rather the emergence of space-time from a pre-existing quantum state? The concept that the universe might have emerged from a quantum vacuum, an emptiness full of fluctuations, introduces a radically different perspective on the cosmos. In classical physics, we tend to think of a vacuum as a completely empty space, devoid of any matter or energy. But in quantum mechanics, a vacuum is far from empty. Instead, it is teeming with tiny fluctuations, temporary changes in energy that spontaneously appear and vanish. These fluctuations, though infinitesimally small, can have profound consequences. They can, in theory, give rise to real particles, energy, and even entire universes. At the smallest scales of the universe, on the order of 10 to the minus 35 meters, the Planck scale, quantum fluctuations dominate. Space and time themselves are no longer smooth, continuous entities. Instead, they are granular, composed of tiny, discrete units. At this scale, the uncertainty principle, first articulated by Werner Heisenberg in 1927, rules. This principle suggests that we cannot simultaneously know both the position and momentum of a particle with complete precision. This uncertainty also extends to energy, allowing quantum fluctuations to occur even in what we consider to be a vacuum. In this quantum view, the entire universe could have originated from a fluctuation in this vacuum state. It might have spontaneously appeared, driven by these quantum fluctuations, as an infinitesimally small bump in the fabric of space-time. From this tiny fluctuation, the universe began to expand, ultimately becoming the vast cosmos we observe today. The birth of the universe, then, might not have required a singular event of creation, but instead could have been a natural outcome of the quantum fluctuations that occur in an ever-changing dynamic vacuum. This speculative idea of the quantum origins of the universe suggests that the Big Bang was not necessarily the beginning of time itself. Instead, it was the beginning of time as we experience it, arising from a deeper, timeless quantum realm. In this view, the concept of before the Big Bang becomes difficult to define. Time, as we understand it, may not have existed before the Big Bang, or at least not in any way that we can comprehend. Vlatko Vedral, a physicist known for his work on quantum information theory, has explored how quantum entanglement, another fascinating quantum phenomenon, might play a role in understanding the cosmos at the deepest level. Entanglement is the process by which particles become correlated in such a way that the state of one particle instantaneously affects the state of another, regardless of the distance between them. This connection, which Einstein famously referred to as spooky action at a distance, challenges our traditional understanding of space and time. Vedral's work on quantum entanglement suggests that the entire universe might be deeply connected in ways that we are just beginning to understand. If the universe emerged from a quantum vacuum, then the entanglement of particles, energy, and space-time could be fundamental to its very structure. This means that the universe's origin might be more deeply intertwined with quantum processes than we ever imagined, with every part of the cosmos connected in a way that goes beyond the observable. The idea that quantum fluctuations could give rise to the universe is not new, but it was given a powerful boost by physicists like John Archibald Wheeler. In the mid-20th century, Wheeler introduced the idea of quantum foam, describing the turbulent, ever-changing fluctuations at the Planck scale. He suggested that space-time itself could be shaped by these quantum processes, with the fabric of the universe emerging from a chaotic, dynamic quantum state. Wheeler famously said, "Space-time tells matter how to move, matter tells space-time how to curve." His insight was that at the smallest scales, space and time are as uncertain as the particles within them. Wheeler's work helped set the stage for modern quantum cosmology, which seeks to understand the birth of the universe through the lens of quantum mechanics. One of the key principles of this field is the idea that quantum effects could have been at the heart of the Big Bang. The universe, as we understand it, could have emerged from a quantum fluctuation in the vacuum, with space-time itself being a product of the underlying quantum forces. This idea transforms our understanding of the universe's origin, moving away from a singular, isolated beginning to a process rooted in the fundamental laws of quantum physics. In this quantum view of the universe's origins, the traditional notion of a singular explosive event is replaced by the idea of an ongoing dynamic process that could have originated from quantum fluctuations in the very fabric of space-time. The Big Bang, in this context, becomes the point where time and space as we know them began to emerge, not the creation of everything, but the beginning of the universe as we experience it. These quantum origins challenge the idea of a fixed, singular origin for the universe. If the universe emerged from a quantum vacuum, then the question of what happened before the Big Bang becomes even more complex. Time itself, as we understand it, may not have existed in the way we experience it before the Big Bang. Instead, the universe could have existed in a timeless quantum state, where the very concept of before loses its meaning. The speculative nature of these ideas might be hard to grasp, but they're grounded in the fundamental principles of quantum mechanics. The fact that the universe could have arisen from a quantum fluctuation, driven by the uncertainty of quantum mechanics, opens up new possibilities for understanding the origins of the cosmos. If we accept that quantum fluctuations can give rise to entire universes, we must also consider that our own universe could be one of many, each emerging from its own quantum fluctuations, each with its own unique set of physical laws and constants. The deeper we delve into these ideas, the more we realize that the universe's origin may be far stranger than we ever imagined. Quantum mechanics, with its strange and often counterintuitive principles, holds the key to understanding not just the workings of atoms and particles, but the very nature of space and time itself. Whether the universe emerged from a quantum vacuum, or whether it's part of a larger multiverse of fluctuating possibilities, the quantum origins of the cosmos continue to challenge our understanding of existence itself. In the end, the Big Bang might not have been a singular moment of creation, but rather the birth of time and space as we understand them. The quantum forces that gave rise to our universe may have shaped not just the cosmos, but the very laws of nature, pushing us to reconsider the most fundamental aspects of reality. Imagine looking at the world around you and suddenly realizing that everything you perceive might not be as solid or as real as it seems. What if the entire universe, all of space, all of time and everything in it, was nothing more than a projection, a shadow, cast from a lower dimensional boundary? This is the essence of the holographic principle, a theory that suggests our three-dimensional reality could be a projection from a distant two-dimensional surface. At first glance, the idea might seem as though it belongs in the realm of science fiction, but it has deep roots in theoretical physics, offering a revolutionary way to think about the nature of the universe. The holographic principle suggests that everything we experience, all the stars, planets, and even time itself, could be encoded on a distant boundary or surface, much like how a three-dimensional image can be projected from a two-dimensional film. In this view, our entire universe, as vast and complex as it may seem, could be a kind of illusion, much like the shimmering image on a movie screen that only appears real, but is actually just a projection of information. One of the most profound implications of the holographic principle is its challenge to our understanding of space and time. For centuries, we have thought of space and time as fundamental dimensions that shape our reality. Space is the stage on which the drama of the universe unfolds, and time is the measure of everything that happens. But what if these ideas are not as fundamental as we believe? What if time and space, as we understand them, are merely projections, higher dimensional shadows cast from a more fundamental level of reality? The theory was given serious consideration by the physicist Juan Maldacena in the late 1990s. Maldacena's groundbreaking work, which became known as the ADS-CFT correspondence, offered a mathematical framework that linked a higher dimensional universe to a lower dimensional one. His work suggested that a universe with gravity, like the one we inhabit, could be mathematically equivalent to a non-gravitational theory that exists on a distant boundary. In simpler terms, Maldacena proposed that all the gravitational effects we observe in our universe could be explained by a theory that exists on a surface at the edge of space-time, meaning our three-dimensional experience of the cosmos could be a projection from this boundary. This radical idea introduced a new way of thinking about space, time, and gravity. If the universe is a projection, then the Big Bang, that monumental event we've always seen as the beginning of time itself, might not be the true beginning of everything. Instead, the Big Bang could simply be the boundary between two different phases of a higher dimensional universe. Rather than being a singular event, the Big Bang might be a transition point, a shift in the way information is encoded and projected into our three-dimensional reality. To understand this better, consider how the universe might look from the perspective of the holographic principle. Imagine that the entire universe is contained on a two-dimensional surface, much like how a hologram is a two-dimensional image that appears three-dimensional when viewed from certain angles. All of the three-dimensional objects in our universe, including stars, planets, and even galaxies, could be the result of information encoded on this two-dimensional surface. Space and time, in this view, are simply projections of this underlying information, much like the way a 3D object can be cast from a 2D hologram. The implications for the Big Bang are profound. If the Big Bang is just the point at which space-time as we know it began to emerge from this boundary, then it's not the true origin of the universe. Instead, it could be a transition, a phase change in a higher dimensional system that causes the universe to expand and evolve. In this context, time itself may be a product of the projection process, emerging only when the holographic information is projected into our three-dimensional space. This idea challenges the very notion of before the Big Bang, because in the higher dimensional reality from which our universe is projected, the concept of time might not even apply. What's especially fascinating about this theory is that it could provide a way to reconcile the two pillars of modern physics: general relativity, which governs the large-scale structure of the universe, and quantum mechanics, which describes the behavior of particles at the smallest scales. In classical physics, these two theories have been difficult to reconcile, but the holographic principle might offer a unified framework that explains both the nature of space-time and the quantum world. As we dig deeper into the idea of the holographic universe, it becomes clear that the theory raises more questions than answers. For instance, if the universe is a projection, what is the nature of the boundary from which it is projected? What kind of physical reality exists at the boundary? And how do the laws of physics work at the higher dimensional level that creates the projections we experience as time and space? These questions are still open, but the holographic principle has opened up new possibilities in our understanding of the cosmos. It suggests that the universe is far more subtle and mysterious than we ever imagined. Time, space, and gravity might not be as fundamental as we thought. Instead, they could be the result of deeper, hidden principles that are yet to be fully understood. Another profound aspect of the holographic principle is its connection to quantum information theory. Quantum information theory studies how information is processed and stored in quantum systems, and it has revealed some surprising connections to the holographic universe. One key idea in quantum information theory is that information about a system, whether it's a particle or a galaxy, can be encoded on a lower dimensional surface. This idea, known as holography, suggests that the universe itself might be a kind of quantum information system, with space and time emerging as a result of the way information is stored and processed at a deeper level. If this idea is correct, then the entire fabric of space-time could be an emergent phenomenon, arising from the quantum information encoded at the boundary of the universe. This view challenges our traditional understanding of space-time as a fundamental stage on which events unfold. Instead, it suggests that space-time is a projection, a shadow cast by the underlying quantum information that governs the cosmos. The implications of this theory are far-reaching. It suggests that the universe may not be a fixed, static entity, but a dynamic process that emerges from quantum information at every moment. Space and time may not be fundamental building blocks of reality, but rather the result of deeper, more fundamental principles that we're only beginning to understand. As we explore these ideas, we come to realize that the holographic principle does more than just challenge our understanding of the universe. It forces us to rethink the very nature of reality itself. If the universe is a projection, then our experience of time, space, and gravity might be just a small part of a much larger hidden reality that we are only beginning to glimpse. In this view, the Big Bang might not be the beginning of the universe, but simply a moment in an ongoing higher dimensional process. This is the beauty of the holographic universe. It invites us to look beyond the surface and question everything we thought we knew about the cosmos. It opens up a new way of thinking about space, time, and reality, one that suggests that the universe we experience is just one small projection of a much deeper and more mysterious world. Picture a universe far beyond our familiar three dimensions. Imagine there are hidden dimensions, folded up and out of our direct perception, waiting to be discovered. This idea is central to string theory, one of the most intriguing frameworks in theoretical physics. In string theory, the fundamental building blocks of reality are not tiny particles, but tiny, vibrating strings of energy. And these strings exist not just in the three-dimensional space we experience, but in additional dimensions that are compactified, meaning they're curled up so small that we can't directly perceive them. String theory suggests that the universe operates in a higher dimensional space, one that includes more than the three dimensions of space, and one dimension of time that we are familiar with. In fact, string theory proposes that there could be as many as 10 or even 11 dimensions, each with its own role in the structure of the universe. These extra dimensions are hidden from us, but their influence could be felt in subtle ways, particularly in the deep workings of gravity and the behavior of elementary particles. The existence of these extra dimensions could provide answers to some of the biggest questions in cosmology, including those surrounding the origins of the universe itself. In fact, many physicists believe that understanding how these extra dimensions work might help us understand the universe before the Big Bang, or even provide a new way of thinking about what happened before the Big Bang. One of the leading figures in exploring the role of higher dimensions is Nima Arkani Hamed, a physicist at the Institute for Advanced Study in Princeton. Arkani Hamed's work focuses on the implications of extra dimensions and how they might help explain the structure of the universe. He, along with other researchers, has proposed that our universe may exist within a higher dimensional space. In this view, what we think of as our three-dimensional reality is just a slice, or a projection, of a much larger, higher dimensional space. Our universe could be like a piece of paper floating in a higher dimensional space, with the extra dimensions hidden from our perception. The existence of higher dimensions might offer new ways to think about the Big Bang itself. Instead of the universe beginning as a singular point of infinite density, as traditional cosmology suggests, the universe could have originated from a higher dimensional space, where the rules of physics are vastly different. The Big Bang could then be seen as a transition, a phase change, when spacetime began to expand and unfold from a higher dimensional state. This would suggest that the pre-Big Bang universe could have existed in a state where the familiar concepts of time and space didn't apply in the way we understand them. In this scenario, the early universe may have been a kind of higher dimensional phase, where extra dimensions played a crucial role in shaping the universe. For example, gravity, as we know it, might behave very differently in a higher dimensional space. In such a space, gravity could be stronger or weaker than we observe in our three-dimensional world, and the way it operates might change as the universe transitions into the three-dimensional space-time we experience today. This could have profound implications for understanding the universe's origin and its evolution. Moreover, the existence of higher dimensions could also provide a potential link to the multiverse. The multiverse theory proposes that there are many universes, each with its own set of physical laws. In some versions of the multiverse, each universe exists in a separate bubble, and these bubbles could be embedded in a higher dimensional space. In this view, our universe would be just one bubble among many, each existing in its own region of the higher dimensional space. This suggests that the Big Bang might not be the creation of the entire cosmos, but just the birth of our particular universe within a vast higher dimensional landscape. One speculative idea is that the pre-Big Bang state of the universe could have been connected to other universes through higher dimensional interactions. Before the Big Bang, our universe might have been in a higher dimensional state, with time and space as we know them not yet fully formed. The Big Bang could then be a birth from this higher dimensional realm, when our universe transitioned into the three-dimensional spacetime we are familiar with. This would challenge the traditional notion of a singular, isolated origin, and instead suggest that the Big Bang was just one of many such events occurring within a larger, higher dimensional reality. This idea is closely related to the concept of brane cosmology, a branch of string theory that suggests our universe might be a brane, a multidimensional object, floating in a higher dimensional space. In this view, our universe is not the only brane, and other branes could exist in parallel, each one with its own set of physical laws. These other branes could be part of a much larger higher dimensional space, and the interactions between these branes could give rise to the Big Bang, as well as the creation of new universes. The speculative potential of higher dimensions doesn't just challenge our understanding of the Big Bang, it also opens up new ways of thinking about the nature of space, time, and reality itself. If the universe exists within a higher dimensional space, then our perception of reality could be limited, and much of what we think we know about the cosmos could be just a fraction of the true story. In this view, the universe is not a static, isolated object, but rather a dynamic, evolving entity that exists as part of a much larger, interconnected system of higher dimensional realms. One of the exciting aspects of these ideas is that they offer potential answers to some of the most fundamental questions about the universe. For example, if the universe originated from a higher dimensional space, then the concept of before the Big Bang may no longer apply in the traditional sense. In higher dimensional space, the Big Bang might not be a singular, unique event, but a continuous process, part of an ongoing interaction between different dimensions and different realms. This idea challenges our conventional understanding of time and causality, and suggests that the universe could be part of an eternal, cyclical process that stretches far beyond the limits of our perception. As we continue to explore the mysteries of higher dimensions, we begin to see how they could offer profound insights into the origin of the universe and its true nature. The work of physicists like Nima Arkani Hamed, who have explored the implications of extra dimensions, provides a new way of thinking about the cosmos. These ideas suggest that the universe is not an isolated bubble in a vast empty space, but part of a much larger interconnected web of higher dimensional reality. The idea that the universe could exist within a higher dimensional space, where space-time and gravity behave differently, is a mind-boggling possibility that could change the way we understand everything from the Big Bang to the future of the cosmos. By exploring the role of extra dimensions, we're taking a step toward understanding the universe's true origins and perhaps uncovering new realms of reality that are beyond our current comprehension. In the end, the true nature of our universe and the question of what happened before the Big Bang may lie not in the three-dimensional world we see around us, but in the hidden dimensions that lie just beyond our grasp. Imagine for a moment that the universe, everything we see, feel, and experience, didn't emerge from nothingness, nor was it created by a singular, explosive event like the Big Bang. Instead, picture the universe as something that emerged from a deeper, non-physical realm, a place that exists beyond the limits of our traditional understanding of space, time, and matter. This is a concept that may seem far outside our everyday understanding, but it's one that has captured the imagination of philosophers, physicists, and cosmologists alike. What if the universe didn't begin from a singularity, a tiny point of infinite density, as traditional cosmology suggests? What if the Big Bang wasn't truly a creation event, but instead a transition, a manifestation of a more fundamental, non-physical reality that existed long before time as we know it? This idea suggests that the universe could have emerged from what might be called a void, or perhaps even a higher dimensional entity, one that lies beyond conventional physical laws and is difficult to fully comprehend using our three-dimensional framework. This line of thinking challenges everything we understand about the beginning of the universe, offering the tantalizing possibility that the Big Bang was not the beginning of everything, but rather a shift in the state of a deeper, more fundamental realm. In this scenario, the universe as we know it could be just one phase or manifestation of a much larger, more complex process that is not bound by the rules of physics that govern our everyday experiences. Philosophers and scientists alike have entertained ideas of the universe originating from non-physical or metaphysical realms. One of the most intriguing concepts comes from the physicist David Bohm, who proposed the notion of an implicate order, a deeper layer of reality that underlies the world we experience. Bohm's theory suggests that the universe, at its most fundamental level, is not as it appears. Instead of being made up of separate, independent objects, everything in the universe is interconnected in a hidden, deeper order. This implicate order is non-physical in nature, and from it the physical world emerges as an explicate order, the world we see around us. According to Bohm, what we perceive as reality is just a surface manifestation of this deeper order, a kind of projection or unfolding of the hidden dimensions of existence. In this view, the Big Bang could be seen not as the creation of the universe, but as a moment of unfolding, a transition from the implicate order to the explicate order, where the non-physical, deeper reality began to manifest as the physical universe we experience. The Big Bang, then, might not have been the birth of everything, but rather the emergence of the physical laws and space-time that define our universe. Bohm's ideas resonate with other speculative theories in cosmology that suggest the universe could have emerged from a non-physical state, one that is not governed by the laws of space and time. These ideas are not simply philosophical musings, but are grounded in serious scientific inquiry. For example, some physicists have speculated that the universe could have originated from a quantum vacuum, a state that exists beyond the traditional framework of space and time, where quantum fluctuations could give rise to entire universes. In this scenario, the universe would not have a singular, unique beginning, but would instead be one of many possible states that could emerge from the quantum vacuum. In this view, the idea of the universe emerging from a non-physical realm is not a rejection of physics, but rather an extension of it. Theories like string theory and quantum mechanics suggest that space and time are not fundamental. They are emergent properties that arise from deeper hidden structures of reality. String theory, for instance, posits that the fundamental components of the universe are not point-like particles, but tiny vibrating strings of energy that exist in higher dimensions. These extra dimensions, beyond the three we experience, could be the source of the universe's emergence. In this sense, the universe could be seen as a projection of a higher dimensional reality, with the Big Bang being a transition from this higher dimensional realm into the lower dimensional physical universe we observe. Furthermore, the concept of the multiverse ties into these speculative ideas. If the universe could emerge from a non-physical or higher dimensional state, then it stands to reason that other universes might also exist, each with its own set of physical laws and properties. The multiverse theory suggests that our universe is just one of many, each potentially having different dimensions of space, time, and fundamental forces. These universes could have emerged from the same non-physical or higher dimensional realm, with the Big Bang being a localized event in the context of an infinite and ever-evolving set of parallel realities. The idea that the universe could have originated from a higher dimensional or non-physical realm also challenges our conventional understanding of time. In traditional cosmology, the Big Bang marks the beginning of both space and time. But if the universe emerged from a deeper non-physical reality, then time itself may have emerged only at the moment of the Big Bang. In this case, asking what happened before the Big Bang becomes a nonsensical question, because time, as we know it, did not exist before that event. Instead, the emergence of time could be tied to the transition from the higher dimensional or non-physical state to the physical universe we now observe. This idea brings us back to the speculative nature of these theories. While they may seem unconventional, they are grounded in serious scientific exploration. As we continue to probe the mysteries of the universe, we are faced with the possibility that the laws of physics we know might not be the ultimate explanation for the universe's origins. Instead, there could be a deeper, more profound layer of reality, a realm that exists beyond the reach of our current scientific understanding. And from this realm, the universe could have emerged, not as a creation event, but as a manifestation of more fundamental, non-physical principles. In the end, the concept of the universe emerging from a non-physical or metaphysical realm forces us to rethink the very nature of existence. It challenges our assumptions about what is real, what is possible, and what it means for something to exist at all. The Big Bang, once seen as the ultimate creation event, might instead be the gateway to a much deeper reality, one that we are only beginning to understand. As we explore these speculative ideas, we come closer to uncovering the true nature of the universe and its origin, and perhaps even our own place within it. Ancient Eastern cosmologies, particularly from Hinduism, Buddhism, and Taoism, offer fascinating and deeply philosophical views on the nature of the universe. These traditions share a belief in cyclical patterns of creation, destruction, and rebirth, which parallel many of the modern scientific models we are now exploring. Far from being just spiritual or metaphysical concepts, these views resonate with contemporary cosmological theories that emphasize cycles of expansion and contraction, the birth and death of universes, and the idea that nothing is truly permanent, but always in a state of flux. In Hindu cosmology, the universe is understood to go through vast cycles called yugas, which represent different ages or epochs. These yugas move through a predictable rhythm of creation, preservation, and destruction. The Kalpa, the day of Brahma, the creator god, lasts for a period of 4,300,000,000 years. After this day, the universe is destroyed, only to be created again in an eternal repeating cycle. This cyclical view of the universe, where creation and destruction happen in an endless loop, mirrors the ideas we find in modern cosmology, especially in cyclic universe theories, such as those proposed by physicists like Roger Penrose. Similarly, in Buddhism, the cycle of samsara, the continuous cycle of birth, death, and rebirth, represents not only the fate of individual beings, but also the unfolding of the universe itself. The Buddhist concept of impermanence suggests that nothing is fixed or permanent, and everything is subject to constant change. This is a key principle that aligns with current cosmological views, particularly when we think about the universe's expansion and eventual contraction in models like the Big Bounce. In this way, the universe may undergo infinite cycles, constantly being reborn in a cosmic dance of destruction and renewal. Taoism, with its emphasis on the balance of forces and the unity of opposites, similarly reflects a cyclical understanding of the universe. The Taoist concept of the Tao, an ultimate principle that governs all things, suggests that the universe is in a constant state of flow with a balance between creation and destruction, the material and the spiritual. The Tao itself is seen as something that cannot be fully understood, yet it drives the constant ebb and flow of existence. This resonates with ideas in modern cosmology, where the universe's laws, forces, and energies are in constant motion and transformation, leading to the birth of stars, the formation of galaxies, and the eventual death of the universe in theories such as the Big Crunch. In a broader sense, these Eastern philosophies propose that the universe is not a one-time linear event, but rather something that is perpetually evolving through cycles. This cyclical nature offers a stark contrast to the Western view of a universe that began with a singular moment, the Big Bang, and continues to expand outward toward an unknown future. The idea that time itself might be cyclical, that it flows in endless loops, can be deeply liberating, as it challenges the traditional linear view of time that we often take for granted in the West. When we compare these Eastern views of time with the Western scientific perspective, the differences become striking. In the West, time has traditionally been seen as linear, moving from the past through the present and into the future. The classical idea of the Big Bang fits neatly into this linear narrative, where the universe had a definite beginning and will likely have a definitive end. However, modern cosmology has increasingly questioned this linear understanding. Theories such as the cyclic universe, in which the universe experiences an infinite series of expansions and contractions, suggest a more Eastern-like view of time. In fact, some physicists like Roger Penrose and Andre Linde propose that the universe could be in an eternal cycle, with the Big Bang being just one phase in a much larger cosmic rhythm. The ideas of cyclical time and the eternal recurrence of the universe also resonate with more contemporary quantum theories, especially when we consider quantum mechanics' treatment of time. Time in quantum mechanics is much less predictable than in classical physics, and quantum theory suggests that, at the very small scales of reality, time may behave in strange and counterintuitive ways. In this sense, the Eastern concept of time as cyclical or eternal aligns with some modern ideas in quantum cosmology, where space-time itself may be a dynamic, evolving entity that doesn't adhere strictly to linear progression. The notion that the universe could cycle through states, constantly transitioning between creation and destruction, mirrors the fluid and unpredictable nature of quantum events, where even the most fundamental laws of physics can bend, shift, and transform. Carl Sagan, the beloved astronomer and cosmologist, was one of the many Western thinkers who found inspiration in Eastern philosophies. Sagan often spoke about the importance of embracing the idea of the universe as a living, breathing entity, a concept that resonates with the Eastern view of a cosmic dance, ever-changing and constantly evolving. His reflections on the universe echoed many of the ancient ideas about time and creation, even if Sagan himself did not explicitly connect them to Eastern philosophies. Sagan's work, especially in advocating for the idea of cosmic interconnectedness, reminds us that the universe is not just a machine, but a vast, interconnected whole, much like the Taoist vision of the universe as a harmonious flow of energy. Alan Watts, a philosopher and spiritual teacher, is another Western thinker who drew parallels between Eastern philosophy and modern science. Watts often discussed how Western science and Eastern spirituality could be viewed as complementary, with both offering a deeper understanding of reality. For Watts, the cyclical nature of time in Eastern philosophies was not just a spiritual idea, but something that echoed the dynamic, ever-changing universe that modern physics is beginning to uncover. In his teachings, Watts suggested that the universe is not a static entity, but a continuous, ever-evolving process, much like the cycles of creation and destruction described in Hindu and Buddhist cosmologies. These insights from Eastern philosophy align remarkably well with modern scientific cosmology, particularly when it comes to our evolving understanding of time, space, and the nature of the universe. Just as Hinduism, Buddhism, and Taoism view the universe as a series of cycles, with creation, destruction, and rebirth happening over and over again, modern science is beginning to recognize that the universe might not be a single, static creation, but a dynamic process that undergoes constant transformation. Whether it's the cyclic universe proposed by physicists like Roger Penrose, the quantum mechanics of space-time, or the multiverse theory suggesting infinite parallel universes, There is a growing recognition that the universe we see around us may not be the final state of reality. Instead, it may be just one cycle in a much larger ongoing process. The universe, like the philosophies of the East, may be a cosmic rhythm, a dance of energy, matter, and time that stretches far beyond our limited understanding. For centuries, we've regarded consciousness as something deeply personal, as something that resides in our minds, a subjective experience that helps us navigate the world around us. But what if consciousness, in a more fundamental way, is not just a product of the brain, but an essential part of the very fabric of the universe itself? What if consciousness played a role in shaping the cosmos, even in triggering its existence? This idea, which might seem more like philosophy than science, is gaining traction in the world of modern physics. It begins with a concept known as the participatory universe, first proposed by the brilliant physicist John Wheeler. Wheeler's ideas radically reshaped our understanding of the relationship between observation, reality, and the universe. He famously said that no phenomenon is a phenomenon until it is an observed phenomenon, suggesting that the act of observation is not simply passive, but plays an active role in determining the state of reality itself. According to Wheeler, the universe might not even exist in the way we experience it unless it is being observed, that is, unless there is consciousness to bring it into being. This speculative theory implies that consciousness is not merely an afterthought in the grand cosmic dance, but could be woven into the very creation of reality. Wheeler's participatory universe suggests that the act of observation, the conscious awareness of an event, is what actually collapses the wave function of quantum mechanics. That is, it determines the outcome of quantum events. Without a conscious observer, the quantum world would remain in a state of indeterminate possibilities. In this view, consciousness doesn't merely experience the universe. It plays an essential role in bringing the universe into existence as we know it. Wheeler's ideas are closely related to the famous double-slit experiment in quantum mechanics, which demonstrates the strange nature of quantum particles. When particles like electrons are not being observed, they behave as if they are waves, existing in multiple states at once. However, when they are observed, they collapse into a definite state, behaving like particles. The fact that observation seems to change the behavior of particles has led many to wonder whether consciousness itself is playing a role in this collapse, shaping the very outcome of reality. The connection between consciousness and the universe becomes even more fascinating when we turn to the work of physicists like Roger Penrose. Penrose is known for his work on quantum gravity and his exploration of the mind-body problem. In his book, The Emperor's New Mind, Penrose speculated that consciousness might be deeply connected to quantum mechanics, suggesting that the brain's processes might involve quantum effects that are far beyond our current understanding. He proposed that consciousness could not simply be a classical phenomenon, that is, a product of neural processes alone, but instead it could be tied to the fabric of the universe itself. Penrose's theories suggest that consciousness could involve a deeper, more fundamental layer of reality, one that is linked to quantum events at the Planck scale, the smallest scale of space-time. In this view, our subjective experience of awareness might emerge from the interaction between the quantum realm and the larger classical world. Penrose's work points to a kind of quantum non-locality, where the mind might not be confined to the brain, but could be influenced by a broader, interconnected reality, a reality where consciousness interacts with the quantum structure of the universe. This opens the door to another speculative idea, that consciousness, in some form, could have played a role in the very creation of the universe. If quantum fluctuations, the tiny random disturbances in energy at the Planck scale, played a part in the emergence of space-time and matter during the Big Bang, could consciousness itself have been a trigger for these fluctuations? Could the very act of consciousness, perhaps in a higher dimensional or non-physical form, have sparked the creation of the universe, setting everything into motion? It's an exciting thought, though deeply speculative, that consciousness might not just emerge from the universe, but be integral to the universe's existence. If consciousness is indeed tied to the fundamental structure of reality, as suggested by both Wheeler and Penrose, then the universe itself might be seen as a kind of vast interactive process, a dynamic system in which consciousness is not just a passenger, but an active participant in shaping and unfolding reality. This perspective is further supported by ideas from quantum mechanics and its philosophical implications. In quantum mechanics, Reality doesn't exist in a definite state until it is measured or observed. The act of observation is often viewed as a way of collapsing the quantum wave function, which suggests that particles exist in a range of probabilities until they are observed. But what if it's not just any observer that collapses the wave function? What if it's conscious awareness itself, the act of conscious observation, that brings the potential into reality, shaping the world in profound ways? The connection between consciousness and the cosmos also touches on deeper philosophical questions. Could the universe itself be conscious in some way? Is consciousness a universal phenomenon, embedded in the very fabric of space-time, waiting to unfold in different forms throughout the cosmos? Some theories of panpsychism, which propose that consciousness is a fundamental aspect of the universe, present even in subatomic particles, suggest that consciousness is not confined to complex organisms like humans, but is intrinsic to all of existence. If this is the case, the universe itself might be seen as a conscious being, in a way that we cannot yet fully comprehend. If consciousness is indeed a fundamental part of the universe, it may be more than just a byproduct of brain activity. It could be an active participant in the creation of reality, an essential element in the process by which the universe comes into being. This concept raises the possibility that the Big Bang itself, as a moment of creation, was not merely a random event, but could have been the product of an intentional or conscious act, or, at the very least, that consciousness played a role in how the universe began to unfold. As we venture further into the realms of quantum mechanics, string theory and cosmology, the idea that consciousness is tied to the very fabric of reality opens up fascinating possibilities. Could the universe have been born in some way through a conscious act? Could consciousness be woven into the underlying structure of space-time, shaping not only the material world but the very rules by which it operates? These ideas challenge our traditional understanding of consciousness and invite us to reconsider the nature of reality itself. Ultimately, the role of consciousness in the cosmos remains one of the most intriguing and speculative questions in science. While we may not have all the answers, the exploration of consciousness and its potential connection to the universe's origins offers a rich field for scientific and philosophical inquiry. As we continue to unravel the mysteries of quantum mechanics, the fabric of space-time and the nature of reality, we might find that consciousness is not just a bystander in the grand cosmic story, but an active, vital force in shaping the universe itself. At the very beginning of the universe, there was a moment of extraordinary and incomprehensible expansion, a brief period where the cosmos grew at an unimaginable rate. This moment, known as cosmic inflation, is one of the most crucial concepts in modern cosmology. It explains how the universe expanded so rapidly during its earliest moments, a phenomenon that would lay the groundwork for everything we see in the universe today, from galaxies to the very fabric of space-time itself. Cosmic inflation is the theory that, in the first fractions of a second after the Big Bang, the universe expanded exponentially, far faster than the speed of light, stretching from a microscopic point to nearly its present size. This process is thought to have happened in a fraction of a second, between 10 to the minus 35 seconds and 10 to the minus 33 seconds after the Big Bang. During this brief but incredibly intense period, the universe increased in size by a factor of at least 10 to the 27th power, meaning that the universe went from smaller than an atom to nearly the size it is today in the blink of an eye. This rapid expansion solved a number of key problems in cosmology that had been troubling scientists. For one, it explained why the universe looked so remarkably uniform on large scales, with galaxies and cosmic structures distributed evenly throughout the cosmos. Without inflation, the universe would be much more patchy, with large regions of matter and energy scattered unevenly. But inflation stretched the fabric of space-time so dramatically that it created a uniform background, smoothing out the universe on the larger scales and giving rise to the even distribution of galaxies that we see today. Cosmic inflation also provided an answer to the flatness problem, which asked why the universe appears to be so perfectly flat, with the sum of its energy density closely matching the critical density required for a flat geometry. Inflation caused the universe to expand so rapidly that any curvature from the early universe was stretched out to the point where it became virtually undetectable, essentially flattening the universe to its present state. Alan Guth, the physicist who first proposed the theory of inflation in 1980, is widely credited with setting the stage for the modern understanding of the universe's early rapid expansion. Guth's original model suggested that the universe underwent an exponential expansion, driven by a type of energy field known as the inflaton field. This field acted as a kind of cosmic fuel, causing the universe to expand rapidly and smoothly. But while Guth's theory laid the groundwork for inflation, it was later work by other theorists, including Andrei Linde, that expanded the idea and opened up new possibilities. Linde, a Russian physicist, refined and extended Guth's model with his own theory of eternal inflation. Eternal inflation takes the concept of inflation a step further by suggesting that the process of inflation is ongoing, that the universe is continually inflating, creating new regions of space-time that undergo their own Big Bang-like expansions. According to this idea, our universe is just one of many pocket universes that have been created by this infinite inflationary process. This could mean that what we think of as the universe, everything we see and know, is actually just one small bubble in an eternally inflating multiverse. In the context of eternal inflation, each pocket universe could have its own set of physical laws. While our universe operates according to the laws of physics we observe, other universes might have different constants, forces, or even dimensions of space-time. This speculative multiverse model offers a potential explanation for the fine-tuning of our universe, the idea that the constants of nature seem perfectly suited for life. Perhaps our universe is one where the conditions just happen to align in a way that allows life, but in the larger multiverse, many universes with different physical laws would be devoid of life. The theory of eternal inflation also offers a new way of thinking about the very beginning of the universe. Instead of the Big Bang being the origin of everything, it might be just the latest event in a never-ending process. In this model, the universe that we observe today might have emerged from a previous inflationary epoch in a different region of space-time. This idea aligns with some speculative models of pre-Big Bang cosmology, where the universe didn't have a singular starting point, but emerged from a continuous process of cosmic inflation that has been happening forever. Quantum fluctuations, which are tiny random fluctuations in energy at the smallest scales of spacetime, also play a crucial role in inflationary theory. These fluctuations were stretched to macroscopic scales during inflation, and as they grew, they became the seeds for the structures in the universe. These fluctuations eventually gave rise to the galaxies, stars, and clusters of galaxies we see today. In this sense, the universe's large-scale structure could be traced back to these minor quantum fluctuations, disturbances in the fabric of spacetime that happened at the Planck scale, the smallest possible scale of spacetime. These quantum fluctuations are crucial in understanding how inflationary theory connects with the very birth of the universe. While inflation was responsible for the rapid expansion, the quantum fluctuations that occurred during inflation were responsible for the uneven distribution of matter in the universe, which eventually gave rise to the formation of galaxies. The clumps of matter created by these fluctuations are the places where gravity would eventually pull things together, forming the dense regions of matter that eventually evolved into the galaxies and stars we see today. But inflationary theory also raises more profound questions, especially when it comes to understanding the pre-Big Bang state. Some theorists have proposed that the concept of inflation could be extended even further to explain the state of the universe before the Big Bang, in a sense that inflation could have been happening before the Big Bang. This might suggest that the universe didn't have a singular beginning after all, but rather that the Big Bang itself was simply the latest phase transition of a continually inflating and evolving cosmos. This view aligns with theories like the Big Bounce, where the universe has gone through infinite cycles of expansion and contraction. This idea also invites questions about the very nature of time and causality. If the universe is part of a process that is eternally inflating, then the idea of a singular origin for time and space might need to be rethought. Perhaps time itself is tied to the inflationary process, with each universe emerging from a kind of eternal flow, rather than having a fixed starting point. This challenges the linear view of time that we often take for granted in both science and everyday life. In sum, cosmic inflation and the role of quantum fluctuations provide one of the most compelling explanations for the origin of the universe. Through the work of Alan Guth and Andrei Linde, the theory of inflation has evolved into a powerful framework for understanding not just the early moments of the universe, but its ongoing existence and possible connection to an eternal multiverse. Inflationary models continue to provide profound insights into the nature of the universe, and they offer new ways to think about the cosmos, not as a singular event, but as part of an ongoing dynamic process that could stretch across infinite time. The universe we observe today might be just one phase in a never-ending cycle, born from the tiny quantum fluctuations that, long ago, set the entire universe into motion. As we look to the future of cosmology, it's clear that we are standing at the precipice of a new era in our understanding of the universe. The mysteries that have eluded us for centuries, the origins of the cosmos, the nature of dark matter and dark energy, and the very fabric of space and time, may soon be within our grasp, thanks to a convergence of cutting-edge technologies and emerging theories. The next few decades in cosmology are likely to be filled with revolutionary discoveries that will reshape the way we think about the universe, its origins, and its future. One of the most exciting frontiers in cosmology is the integration of quantum computing and artificial intelligence with the study of the cosmos. Quantum computing, which leverages the principles of quantum mechanics to perform calculations at speeds far beyond the capabilities of classical computers, holds the potential to transform how we process and analyze the vast amounts of data collected from cosmological observations. With quantum computers, scientists may soon be able to simulate the behavior of the universe at a level of complexity that was previously unimaginable, unlocking new insights into the early universe, the behavior of quantum particles, and even the fundamental nature of space and time. Artificial intelligence, AI, is another powerful tool that is beginning to make waves in the field of cosmology. AI algorithms are already being used to sift through enormous datasets from telescopes, like the Sloan Digital Sky Survey, helping scientists identify new galaxies, stars, and even exoplanets. AI's ability to recognize patterns in data is proving invaluable in uncovering hidden relationships between the universe's vast components. As AI becomes more advanced, it could help us identify previously unnoticed phenomena, suggest new theoretical models, and even predict cosmic events that could change our understanding of the universe's evolution. These advances in computing and AI are also poised to work hand in hand with some of the most ambitious projects in modern astronomy. One of the most exciting tools currently in operation is the James Webb Space Telescope, which, since its launch, has been providing astronomers with unprecedented views of the universe. Positioned far beyond the reach of the Hubble Space Telescope, Webb's infrared capabilities allow it to peer into the deepest corners of space and time, observing the formation of the earliest galaxies, stars, and even the very first moments after the Big Bang. The insights that Webb provides could offer crucial clues about the origins of the universe and help refine existing models of cosmic inflation and the structure of the early universe. Looking even further ahead, upcoming quantum technologies promise to further our understanding of space-time and the nature of reality. Quantum sensors, for example, are being developed to measure gravitational waves with unprecedented precision. Gravitational waves are ripples in space-time caused by violent events, such as black hole mergers or the formation of galaxies. Detecting and studying these waves can provide us with information about some of the most extreme environments in the universe, offering a unique window into the early universe and even the nature of black holes. As quantum sensors improve, they could open up entirely new ways of observing and understanding the cosmos, helping us answer long-standing questions about the fabric of space-time and the birth of the universe. At the same time, breakthroughs in quantum information theory are beginning to suggest that the very fabric of the universe might be more interconnected than we've ever realized. Quantum information theory explores how information is stored and processed in quantum systems, and it has been instrumental in understanding phenomena like quantum entanglement. This theory suggests that space-time itself might not be a continuous, smooth structure, but rather an emergent property of quantum information. In this view, the universe might not be as solid as we think. Rather, it could be a vast network of interconnected quantum states. This could have profound implications for our understanding of the universe's origins and its connection to other potential universes in the multiverse. Indeed, quantum information theory could also help us unlock the mysteries of the pre-Big Bang universe. Some models suggest that before the Big Bang, the universe existed in a quantum state where traditional concepts of time and space didn't apply. Theories like loop quantum gravity and the multiverse hypothesis propose that the universe could have emerged from a quantum fluctuation, an event that triggered the Big Bang. As quantum computers become more powerful, they could help simulate these early quantum states and provide insight into how the universe transitioned from a quantum vacuum to the large-scale cosmos we see today. The concept of the multiverse, which has been gaining traction in recent years, is another avenue where new discoveries could dramatically change our understanding of the universe's origin. The multiverse theory proposes that our universe is just one of many, each with its own set of physical laws and constants. Some of these universes could have been created by quantum fluctuations, as proposed by Andre Linde's theory of eternal inflation, which suggests that inflationary expansion never truly ends, creating an infinite number of universes in different regions of space-time. If this is true, then the universe we see today may be just one bubble in a much larger infinite multiverse, where the Big Bang is not a unique event, but part of an ongoing process of creation. While the multiverse remains a speculative idea, new observations and advances in theoretical physics could soon provide evidence for or against its existence. Projects like the James Webb Space Telescope, along with advanced simulations powered by quantum computing, may give us the tools to test the boundaries of the multiverse hypothesis and uncover evidence that could point to the existence of other universes beyond our own. The discovery of even indirect evidence of the multiverse would be a groundbreaking moment in cosmology, offering new perspectives on the universe's origins and its relationship to other possible realities. These potential breakthroughs in cosmology and physics are just the beginning. As we push the boundaries of technology and theoretical understanding, we are likely to encounter entirely new ways of thinking about the cosmos. The quest to understand the universe's origin, whether it's through quantum fluctuations, multiverses, or the deepest corners of space-time, is a journey that will continue to unfold over the coming decades. With the advent of quantum technologies, artificial intelligence, and powerful telescopes like Webb, the next few years could bring insights that revolutionize our understanding of the universe and our place within it. As we stand on the brink of this exciting future, it's clear that the journey of cosmology is far from over. The mysteries of the universe are vast, and while we've made incredible strides, we're only just beginning to scratch the surface. The answers to the deepest questions about the origin of the universe, the nature of time and space, and the possibility of other realms beyond our own may be closer than we think, and they may change our understanding of everything we thought we knew. As we look deeper into the cosmos, we encounter a fascinating paradox. On one hand, our technological advancements have allowed us to peer farther into the universe than ever before, unveiling the farthest reaches of space and tracing the universe's history back to its earliest moments. Yet, on the other hand, there are limits to what we can observe, especially when it comes to the very earliest stages of the universe, the moments before and immediately after the Big Bang. Current observation technologies, though incredible, face significant limitations in studying the universe's infancy. The primary challenge is that we can only observe what light or other forms of radiation have been able to reach us. This means that our observations are effectively cut off after a certain point in time. The first few moments after the Big Bang remain hidden from our view, and while we have made tremendous strides in understanding the early universe, the full picture is still out of reach. One of the most important tools we have in studying the early universe is the cosmic microwave background, or CMB. This faint radiation, which was emitted when the universe cooled down enough for atoms to form, provides a snapshot of the universe approximately 300,000 years after the Big Bang. By studying the CMB, scientists can learn about the conditions that prevailed in the very early universe, such as the distribution of matter and the seeds of the large-scale structures we see today. The CMB is like a photograph of the universe's infancy, giving us a glimpse into its early state. However, the CMB only tells us about the universe at a later stage, well after the initial moments of the Big Bang. The universe at that time was still extremely hot and dense, with all matter in a uniform state of plasma. This means that while the CMB provides us with crucial information, it also comes with its own set of limitations. It doesn't directly reveal what happened in the moments immediately following the Big Bang, when space-time itself was forming. To learn more about those first moments, scientists must rely on other forms of indirect evidence. One such tool is the study of gravitational waves, which are ripples in the fabric of space-time caused by the acceleration of massive objects, such as colliding black holes or merging neutron stars. Gravitational waves offer a unique way to observe the universe, as they travel through space-time without being absorbed or scattered by matter. When it comes to understanding the early universe, gravitational waves could carry information from the very first fractions of a second, providing insights into events like cosmic inflation or the behavior of space-time during the Big Bang. The detection of gravitational waves from the early universe is still in its early stages, but projects like the Laser Interferometer Gravitational Wave Observatory, LIGO, and the upcoming space-based observatories are expected to push the limits of what we can observe. These waves, though incredibly faint, could offer direct evidence of cosmic inflation or help us understand the fundamental properties of space-time itself. Despite these technological advancements, we must also acknowledge the philosophical limitations of empirical observation in cosmology. No matter how advanced our instruments become, we are still bound by the limits of what is observable. When we study the universe's earlier stages, we're ultimately dealing with indirect evidence, data gathered through light, radiation, or gravitational waves, all of which are affected by the passage of time and the vast distances involved. There are things that may forever be beyond our reach, particularly when it comes to understanding the very origin of the universe. This is where imagination and theory come into play. While our observations give us the pieces of the cosmic puzzle, it is theory that helps us fit those pieces together. Theories about the pre-Big Bang universe, cosmic inflation, and the multiverse are speculative but grounded in the best available evidence. These theories provide us with frameworks for thinking about what might have happened before the Big Bang, even if we can't directly observe it. In this sense, imagination plays a crucial role in pushing forward our understanding of the universe, helping us to propose models that can be tested and refined with future observations. As we continue to explore the early universe, we must also consider the role of quantum mechanics in shaping our understanding. Quantum theory tells us that at the smallest scales, space and time behave in strange and unpredictable ways, which challenges our classical understanding of how the universe works. The concept of quantum fluctuations, tiny random disturbances in energy at the smallest scales, suggests that the very fabric of space-time could have emerged from these fluctuations, leading to the creation of the universe itself. While we cannot directly observe these fluctuations, they are a key part of many theoretical models of the universe's origin. The idea that some aspects of the universe's origin may forever remain beyond the reach of observation is a humbling one. It reminds us that, as much as we've learned, there are still vast mysteries that may never be fully understood. Perhaps the ultimate question, what happened before the Big Bang, is one that we will never be able to answer with certainty. Yet, this does not diminish the importance of the journey. Every piece of data we gather, every theory we test, brings us closer to understanding the cosmos in ways we could not have imagined before. In a way, the limitations of observation also highlight the vastness of the universe and the mystery that surrounds it. As we continue to observe and theorize, we may come to understand that the universe is not a simple, knowable entity, but something far more complex and elusive. The limits of what we can observe should not be seen as barriers, but as invitations to explore new ideas, new ways of thinking, and new technologies that will push the boundaries of our knowledge even further. Ultimately, the pursuit of cosmology is not just about solving specific puzzles or finding answers to long-standing questions. It is about expanding our understanding of the universe and recognizing that some questions may never have a definitive answer. The mystery of the universe's origins and the limits of what we can observe reminds us of the vastness and complexity of the cosmos. And as we continue on this journey, we find that the pursuit of knowledge itself is one of the greatest wonders of all. The story of cosmology is one of evolution, where our understanding of the universe has changed drastically over time. What began as speculative philosophy has transformed into a sophisticated scientific discipline, driven by observations, data, and theories that continue to evolve as we uncover more about the cosmos. One of the most profound shifts in cosmology came with the realization that the universe was not static as previously believed, but expanding. This discovery reshaped our entire understanding of the universe's origin, setting the stage for modern theories, including the idea that the universe's origin may not be a single, isolated event. For much of history, the prevailing view of the universe was influenced by ancient and medieval philosophers who imagined the universe as static, eternal, and unchanging. In this model, the universe had no beginning or end. It simply existed, and everything within it followed a predetermined, unchanging order. This was largely consistent with the ideas of the Greek philosopher Aristotle, whose influence persisted for centuries. But this static view of the universe began to unravel in the early 20th century as new discoveries began to challenge the accepted model. In 1929, astronomer Edwin Hubble made an observation that would alter the course of cosmological theory forever. He discovered that galaxies were moving away from us, and the farther away a galaxy was, the faster it was receding. This observation, known as Hubble's law, suggested that the universe itself was expanding. If galaxies were moving apart, this meant that the universe had to have been much smaller, denser, and hotter in the past. This was the first major step in moving away from the idea of a static universe and towards the notion of an expanding universe. The realization that the universe was expanding set the stage for what we now call the Big Bang theory. The Big Bang theory proposed that the universe began as an infinitely small, hot, and dense point, often referred to as a singularity, around 13.8 billion years ago. From this singularity, the universe rapidly expanded, cooling and forming the stars, galaxies, and planets we see today. This model of the universe's origin was revolutionary and became the foundation of modern cosmology. It introduced the idea of a definitive beginning to the universe, and it was further supported by the discovery of the cosmic microwave background radiation in 1965 by Arno Penzias and Robert Wilson. This radiation, a faint afterglow of the Big Bang, provided compelling evidence that the universe had a hot and dense beginning. Yet, even as the Big Bang theory gained widespread acceptance, questions about the pre-Big Bang universe remained unanswered. What came before the Big Bang? What was the state of the universe before time and space as we know them emerged? These questions have led to the development of a range of speculative theories that continue to evolve with new data and models. Today, cosmologists are pushing the boundaries of our understanding, suggesting that the origin of the universe might not be a singular, isolated event, but rather part of a much larger, ongoing cosmic process. One such theory is cosmic inflation, proposed by Alan Guth in 1980. According to the theory of inflation, the universe expanded at an exponential rate during the first fractions of a second after the Big Bang. This rapid expansion explains several key features of the universe, such as its large-scale uniformity and the distribution of galaxies. However, inflation also suggests that the universe might have emerged from a quantum fluctuation in a much larger, higher-dimensional space. In this view, the Big Bang was not a true creation event, but rather a transition from a quantum vacuum into the expanding three-dimensional universe we observe today. This idea challenges the traditional notion of a singular beginning and opens the door to the possibility that the universe's origin could be part of an eternal cycle of creation, expansion, and contraction. Further pushing the boundaries of our understanding, Andre Lin's theory of eternal inflation introduces the idea that inflation never truly ended, but continues in different regions of space-time, creating new pocket universes. Each pocket universe, or bubble, could have different physical properties, leading to the possibility of a multiverse. In this model, the Big Bang would not be the beginning of all existence, but rather one of many births in an eternal inflating cosmos. Lin's work builds on the idea of cosmic inflation, but extends it to suggest that the universe is not a unique, one-time event, but part of a never-ending process that produces an infinite number of universes, each with its own set of physical laws. These ideas raise fundamental questions about the nature of time and causality. If inflation is an eternal process, and if the universe is part of an ongoing cycle of births and deaths, then the very notion of a singular origin becomes problematic. The idea of a pre-Big Bang universe might not be meaningful in this context, as time itself could have emerged with the process of inflation. In this view, the Big Bang is not the beginning of time, but the moment when time, as we experience it, began to unfold. One speculative model that fits within this framework is the cyclic universe theory, which posits that the universe undergoes infinite cycles of creation, expansion, contraction, and rebirth. This model is reminiscent of ancient Eastern philosophies such as Hinduism and Buddhism, which view the cosmos as a series of cycles rather than a singular event. The cyclic universe theory suggests that the Big Bang was merely one phase in a never-ending sequence of cosmic cycles, each one following the same pattern of birth, death, and rebirth. As cosmological theories evolve, so too does our understanding of the universe's origin. The discovery of dark matter and dark energy has added another layer of complexity to our understanding of the universe's evolution. These mysterious components make up about 95% of the universe's mass-energy content, yet we cannot observe them directly. The role of dark matter and dark energy in the early universe, and their relationship to cosmic inflation, remain open questions, but they will likely play a significant role in future theories of the universe's origin. Emerging ideas in quantum gravity, string theory, and the search for a unified theory of physics also promise to shed light on the pre-Big Bang universe. As we learn more about the quantum nature of space-time, it's possible that we will discover new ways to describe the birth of the universe and the forces that governed it. Quantum technologies such as quantum computers are expected to accelerate our ability to simulate complex cosmological models, providing deeper insights into the earliest moments of the universe and potentially revealing new theories about its origin. The future of cosmology, therefore, is not just about answering the age-old question of where the universe came from. It's about re-evaluating our assumptions about the universe's beginning and its ongoing evolution. The very idea of a singular origin may become obsolete as we explore models that view the universe as an eternal, evolving entity, one that is shaped by processes beyond our current understanding. In this sense, the universe's true origin may not be a single event, but rather a never-ending story of creation, destruction, and rebirth. As new data and theories emerge, we will continue to rewrite the history of the cosmos, moving ever closer to understanding the mysteries of our existence.